Greetings. Today I will tell you things about the so-called least access problem. Which might or might not be justified from the practical point of view, but it's quite interesting. How can one prove the competitive ratio of one of the algorithms for this problem? So in this problem we have say a parameter m, which is just an integer greater than 1, and we manage a list of m items. So we manage well, it's a linked list, so let's say this. So it's linked, a one-way linked list of m items. Now, what the items are, it's actually not that important. So usually with the initialization is initialization. It's just that the list has the elements 1, 2, 3, 4, and so on till m. Now we won't change the list elements themselves. We won't insert new elements to the list. We won't erase elements from the list. We will only rearrange the list, because an input, so a request, is just a query for one of these elements. Okay. Now the cost for serving the request is the position of the request in the list, the position. So if the item happens to be the first element of the list, then we have to pay 1. If it's the last element of the list, then we pay m unit of cost. So the position of sigma I in the current list. And between queries we can rearrange the list. So between queries we can rearrange the list. So there are two options in the basic model. First is we can swap two adjacent elements. So we can swap two elements which are adjacent in the current list. Adjacent elements of the list. Well, of course, this has a cost, for a cost of 1. So it's a unit cost operation. And then, second option, we can move the most recently accessed element to the front, to the beginning of the list, to the front of the list. Now it's for free. For a cost of 0. And that's all we can do. Now let's see an example. So of course the aim is to minimize the total cost, and of course if it's online, then if you serve sigma I, then they don't know whether there will be any more requests and so on, as usual. So minimize the total cost. Now let's see an example. So just to have a better grasp on the problem, so we can just, so for example, if say m is 3 and the input sequence is, let's say, 3 2 3 2, then this means that initially I have linked list 1 2 3, and there is of course an option of never rearranging the list. So if I don't rearrange the list, then for accessing the 3, I will have to pay 3 money, 3 amount of cost, I say. Okay, then for 2 I will have to pay another 2. That's great. And then I'm not touching the order of the elements, because why should I? And then I can just for serving the third request I will pay plus 3, so I'll get to 1 2 3, of course. And then for serving the last request I will also pay 2, because it's the second element in the list at this time, so it's just 1 2 3. And the total cost in this case, if I don't make any rearrangements, is 1 plus 2 plus 3 plus 2, so the total cost, if I do this, then it's 10. Now another option would be just say, okay, so let's try to minimize this. This is quite pricey, because this element 1 is always increasing the cost by, say, at least 1. So we can do just say, let's swap these two elements first before serving the request for 3, and I will have these 2 1 3. Of course this is an operation having a cost of 1, so it's a swap, right? And then I will serve this 3, so I will have a cost of 3 for that, and I will just move to front. That's the shorthand for this operation of moving to the front, which has a cost of 0, so I'm just adding this just to indicate that there is an operation having some associated cost, but in this case the cost is 0. So I pay 3 because the item 3 is the third in this order, and then I'm moving this element 3 to the front, and I will get the 3 2 1. Okay, and then let's say I'm not touching the list anymore, so it's just okay, again accessing the 2 is just a plus 2 cost, and then I'm not changing the order of the list, and accessing the 3 is just plus 1 in this case, and then I access the 2, which is again cost of 2, because that's the second element of this guy. So 3 2 3 2, that was the final guy, and I'm not touching the order of the elements. Now in this case I will get 1 cost for the swap, 3 plus for accessing the element 3, and then I'm having plus 2, this is 6 already, plus 1 is 7, and plus 2 is 9. So in this case, if I'm paying for a swap, then I can just get I can just get the cost of 9 using swaps and the movements to the front. But even better if I'm just changing the order of the elements for like swapping the first two elements. They're the same, so that's also an option. So plus say swap, plus 1 swap, and then I'm again swapping these two elements just before serving the first query, so it's again plus 1 for swap, and then I'm making the then I'm serving the request 3232 in under, so it's 3232, and I'm just not writing down the list again and again since it's not changing, so it's plus 2 plus 1 plus 2 plus 1, because this is the second element, the first element, the second element, and again the first element. And in this case I will get 6 from here and an additional 2 from the beginning, so it's just the cost of 8. So it might be beneficial, so it can pay off to use swappings, non-free swappings, even in the preliminary stage. Now, for this problem, we don't really have any good lower bound for the costs, because, well, yeah, it's quite hard to optimize the total cost, and we can have an even weirder cost functions and weirder operations. Now, there is a thing which nevertheless I will prove, which is the following. So there is no algorithm, deterministic online algorithm, having a better competitive ratio than 2. So there is a statement, so there is no deterministic online algorithm for the least access problem, least access problem with competitive ratio strictly better than 2. So there's the statement, and I will prove this. So proof. So first, if A is any deterministic online algorithm, we can do the same thing as we've done in the analysis of the paging algorithm. So we can always query for the element which is currently is the last element of the list. So if A is any deterministic, and that's important here because I'm constructing a bad enough input based on the behavior of the algorithm, and I have to construct this input in advance, but I'm only able to construct the input in advance if the algorithm is deterministic, because in that case the algorithm will behave all times the very same way, and if it's randomized then I cannot do this. So if A is any deterministic online algorithm, then for any, say, n, and m, n is the size of the input, the number of requests, we can construct a bad input on a bad input with n elements, or request queries, whatever, for A specifically, just always request the last element of the list. Always requesting the last element of the list. Now in that case, one request will have a cost of m because, well, serving the request which asks for the last element of the list, and the list is a list of length m, so I have to pay m. So in this case the total cost is m times n, because I have n requests and each request will have a cost of m at least. Now, why I'm saying at least, because it might happen that the algorithm A uses swaps as well, and in that case it will pay even more. But m times n is a lower bound. Now we will prove that around the half of this quantity is always sufficient. So we will prove that paying, well, around m times n half is sufficient. It's always sufficient. Now the trick is that we will run two algorithms, and the total cost paid by the two algorithms divided by 2, so the average cost paid by the two algorithms, is always at least as large as the minimum of them, which means that the minimum is at most the half of the price the two algorithms pay, which means that the optimum is might be even smaller. So how? We consider two algorithms, and the better among these two algorithms will pay only around half of this cost. So we consider two algorithms. So let's say this A1 never rearranges, the input. So for this algorithm, the cost for serving sigma I is sigma I, of course, because if you request for 1, the algorithm will pay 1. If you just request for 2, then the algorithm will pay 2, and so on, which means that the total cost of A1 is just the sum of these sigma i's. Yeah? Okay, that's always the case. Now A2 is the one which reverses the list in first by swaps, and then doesn't do rearrangements. Now in that case, for example, say if m equals 5, let's see how this rearrangement works. So I'll just have 1, 2, 3, 4, 5, okay, and I'm just swapping these two entries, so it's 1, 2, 3, 5, 4, and I'm just swapping again the 5 just moving it closer and closer into the place. So if you had some sort of algorithms course during your previous studies, then it's just the bubble sort, and the bubble sort has a quadratic time bound. So it's just after 4 steps I will have the 1, 2, 3, 4 just placed after the 5, so it's just the cost of 4, and then to move the 4 here I will have to make 1, 2, 3 steps, so it's just plus 3 steps, so it's just 5, 4, 1, 2, 3, and then for 2 coasts, and then for plus 1 coast I will have the rest reversed, right? So it's 5, 4, 3, 2, 1. 3, 2, 1. Okay, never mind. So it's for a cost of 10 in this case, and of course the reverse cost is just the reverse cost plus, now if I have this 5, 4, 3, 2, 1, then for the 5 I will pay 1, for the 6 I will pay 2, for the 3 I will pay 3, for the 2 I will pay 4, and for the 1 I will pay 5, and of course the sum of these things is always 6. So in general, for each sigma I, so the cost of sigma I is just m plus 1 minus sigma I, right? So it's just 6 minus the requested element, that's the cost of the operation. So the reversal plus the sum for each input requests, the sum of m plus 1 minus sigma I. Now the cost of reversal, what's this? So I have to pay m minus 1 for placing the last element to the front, plus m minus 2, plus blah 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 plus 1. Now this is of course an arithmetic sum, it's the sum of an arithmetic progression, which is, okay, I'm just switching colors, which is just, so it's, in general it's m times m minus 1 half. So for example in the case of 5 it was 5 times 4, which is 20, divided by 2 is 10, right? So that's 10. Okay, so this is how you sum arithmetic progressions. So it's just m times m minus 1 divided by half plus the sum of these m plus 1 minus sigma i's. Okay, so we have this cost for the first algorithm, that cost for the second algorithm, and now of course the optimum is at most the minimum of A1 and A2. Well, most probably none of these two guys is optimal, but of course the optimum is smaller than or equal to any other solution. Now for the minimum, this is of course smaller than or equal to the mean of these two values, of course. So since if these two things are equal, A1 equals A2, then both of the minimum and the mean is A1, and otherwise the minimum is always below the mean strictly. Now this is something I can compute actually, the mean, because if I'm just writing here, it's just I equals 1 to n sigma I, that's the first term, okay, plus, I'm just changing the order of these things, sum from I1 to n is just m plus 1 minus sigma I, okay, plus the cost for bubble sorting those things, m times m minus 1 divided by half. Yeah, Now here, what do I have? Oops, I forgot to divide it by 2. Yeah, so this is divided by 2. Now here in the box, what do I have is just a sum of n elements sigma I plus m plus 1 minus sigma I, so the sigma i's nicely cancel out each other, which means that here I'll have the sum from 1 to m plus 1 plus this m times m minus 1 half. Yeah, that's great. Now of course the sum of n addends, each being m plus 1, is just n times m plus 1 plus this m times m minus 1 half. Okay, so this is an upper bound for the optimum, which means that if I'm just dividing, so the algorithm's cost divided by the optimal cost is at least as large as m times n, because the algorithm's cost was m times n for this particular input, divided by something which is a lower bound, which is an upper bound for the optimum, because the optimum is smaller than this thing, so the fraction will be smaller if I'm just replacing the optimum with this bound. So it's n times, I'm just writing these things out, plus n plus m square half minus m half, and dividing by 2 the denominator is just the same as multiplying by 2 the denominator. And so if n and m tend to infinite, then this cost is not that much, so it's just okay. So what should we do here? So if say I'll make first the length of the input to be quite large, so n is just, sorry for that, so if I'm just switching back, so I have this fraction, and if I say that n, I'm just making this large enough just to make sure that the terms cancel out each other nicely, so it's just say let's see, m half. Okay, so what should I write here? Well, why not? It might be, say, m square divided by 2 plus m divided by 2. Why not? I'm just trying to cancel out this part of the denominator, then it's something like, so it's just, okay, so it's just 2 times m times n divided by m times n plus, okay, so it's m square half plus m square half, which is plus simply m square, and it's plus m half minus m half, this cancels out, so it's just, okay, I can just divide by m, so it's just cancellation, so it's 2n divided by n plus m. Well, here I can just write back this expression in place of n, and I will get m square plus m divided by 2 multiplied by 2 divided by, say, m square half plus m half plus m, which is just 3 over 2 m's. Yeah, that's great. Now again, I can cancel, say something like m square, so it's 1 plus 1 over m divided by m square, so it's 1/2 plus 3 over 2 m's. And if m tends towards infinite, then it tends to 2. 1 divided by 1/2 is just 2. So this means that there is no algorithm which can produce consistently better than 2 competitive ratio for any possible input size. Actually, it can be proved that it's just like 2 minus something, so it's just not that hard. So if you just work a bit with this fraction and just multiply the thing with 2 just to have some nice numbers, not fractions, so it's just 2 plus 2 then by m, and 1 plus, well, it's 3 over m, which is just, say, 2, but 2 would make the denominator to 2 plus 6 over m, so it's just minus 4 over m, like this. So this is just so this says that for any possible m there is no, so a fixed m, there is no algorithm having a better competitive ratio than 2 minus 4 over m, and this can be improved by choosing a different m. But if you just move m towards the infinite, then it turns out that the same expression just converges to 2 from below, of course, but it means that there is no online algorithm which is a better algorithm than 2 in terms of competitive ratio. Okay, now one possible online algorithm for this problem for list access is the so-called move to front algorithm, or we can make a shorthand, so move to front, MTF for short, which just moves the requested element always to the front for free, which moves the requested element always to the front of the list. Okay, so for example, if I have the m equals 3 scenario with this sigma equals 3, 2, 3, 2 guy, then what do I have? So I would have this 1, 2, 3, and then 3 is requested, so it's plus 3, but it's just moved to the front for free. Okay, so it's just 3, 1, 2. Then the 2 is requested, so it's again a cost of 3 and moving to the front for free, so it will have 2, 3 and 1. That's great. And then 3 is requested, and this time it's in the second position, and we move it to the front, which is of course a bad decision for this particular input, but well, the algorithm works this way. So 3 is moved to the front, and then order of the other elements is not changed. So for example, if I move this 3 here, then the 2, 1 will remain in the same order than they were. So the moving to the front was 3, and accessing the element 2 is all again having a cost of 2, and the move to front operation costs nothing. So we have a total cost of 10. Okay, so it's not always optimal, but we can say that there is another statement, is that the move to front algorithm is too competitive for any, of course, competitive, or for any possible input size. Now I will prove this, but to make the video, well, short enough, it's already over half an hour, I'm stopping here, and in the next video I will include the proof of this fact, MTF being too competitive. Till then, bye bye.